Alright gang, in this lesson let's go through Hess's law. This is one of the important tools for us to use. We're learning it now in the Thermo 1 unit, but the things I'm going to say right now, I'm going to go through it using enthalpy, but I want you to keep in the back of your mind that Hess's law works for more than just enthalpy. It works for all the thermodynamic functions, including ones we'll learn about in Thermo 2, like entropy, Gibbs free energy, and it even works in electrochem as well. The premise behind all this is the question, how do we actually find or measure enthalpy changes? We've already talked about using calorimetry. We can actually go to the lab, we can combust something, for example, and we can use a calorimeter to measure the change in temperature of usually water or something. And we can actually use delta T, change in temperature values, along with our equation, Q equals MC delta T, to find enthalpy changes. So we could actually measure it. That's one way. But some reactions are very difficult to measure changes in temperature. There's lots of examples of that. If your system is composed of aqueous ions or gases, it's very difficult to stick a thermometer up against a gas. Like think back to something you've seen in pre-AP. You've all seen the demo where we take a ribbon of magnesium, a little strip of magnesium, and we burn it, and it gives that bright flash of light. Well, that's an example of a reaction where it would be very difficult to measure the change in temperature, because how do you stick a thermometer up against that burning magnesium and either not have it break the glass or lose all the heat to the surroundings without going directly into the thermometer? So it's very tough. Again, some reactions are just very difficult to take delta T measurements. So when that's the case, we have other options. We can use delta H of previously established reactions. These reactions may be some that are either done before very carefully and have been stored in some sort of table, or they could be reactions that are based on formations of different elements. So a couple different types of ways we can do this is using heats of formation. These will be using values for each compound that you're looking at. It would be how to make that compound from its constituent elements in the standard state. For example, if you want to look at CO2, it would be carbon plus oxygen forms CO2, and you can use the table values for that. We'll do that in a subsequent video. But in this video, I want to look at Hess's law. Hess's law allows us to take enthalpies from previously measured enthalpy from reactions. And these reactions can be reactions that have nothing to do or have no direct relationship. Now, let me rephrase that. These could be reactions that don't look like the steps that you're actually taking. They could be from just closely related steps. That probably doesn't make a lot of sense right now. But let's look at Hess's law. Hess's law actually states when reactants are converted to products, the change in enthalpy is the same whether the reaction occurs in one step or it is a series of steps. The enthalpy change only depends on the final and initial states. This is a restatement of what we've learned about state functions. Enthalpy is a state function. If you look at the little diagram here, you can see that going from A to D would be a one-step process, or you could do this in a series of steps going from A to B, B to C, and then C to D. If you added up the enthalpy for A to B plus the enthalpy change for B to C plus the enthalpy change for C to D, they would all equal the same as just delta H from A to D. So it doesn't matter if you do it in one step or three steps, because enthalpy changes are state functions, you'll get the same answer. So how do we actually manipulate Hess's law? Hess's law, to work these problems, we're going to take a series of steps, and then we're going to add up the steps together to get an overall reaction. So we're going to manipulate each step in some algebraic function. That means maybe multiplying the whole thing by 2, or dividing it by 3, or something simple like just reversing it. The thing we have to remember, though, whatever we do to the reactants and products, we have to remember to do it to the enthalpy. So let's try a couple of examples. In this example, we're trying to get the reaction given here. P4O6 plus 2 oxygens goes to P4O10. We're given a couple of different reaction steps, maybe are from a book. Some chemist has already done these steps and recorded the enthalpy change. So let's take these two steps and let's manipulate them so that we add them together to get the overall reaction that I put a star next to. This one's really easy. And what I suggest you do is look at what you're trying to accomplish. Like for example here, I want P4O6 on the reactant side and I want one of them. Look at your steps, find that. Here's P4O6 here. You can see that it already has a coefficient of 1, so that's really good, but it's on the wrong side. So let's take that first step here and let's just flip the thing around and let's get P4O6. And I'm not going to write all the solid stuff. We can come back and put that at the end. P4O6 goes to P4 plus 3O2, so it didn't change anything. I just flipped it around, so I need to take that enthalpy, and here's what students usually forget. Make sure if you reverse the reaction, the enthalpy is also going to reverse, so this becomes now positive 1640.1 kilojoules. Okay? Now, the other kind of unique species in this reaction is P4O10. That occurs only in step 2. It's already the proper coefficient and it's already on the correct side. So I don't really need to do anything probably to this reaction. I'm just going to write it down. P4 plus 5O2 goes to P4O10. And since I didn't do anything with the delta H, I'm just going to bring this enthalpy value along for the ride. And then let's add them up and make sure that everything cancels out properly. I have a P4 as a reactant and a 1P4 as a product, so those will cancel out. I have oxygen on both reactant side and on the product side. They're not the same number, but the 3 oxygens here will cancel out with the 5 here and leaves me with 2. So in my overall reaction, I'm left with 2 oxygens. I'll bring the P4O6 down. There's my yield sign. And then the P4O10 is brought down as well. And that is the overall reaction that we were looking for. But we wanted to get the enthalpy, so we're going to do the same thing. We're going to add up the 2 enthalpy values we've gotten. And that comes out to be, if I did my math correctly, negative 1,300 kilojoules. And for sig figs, that last 0, it should be 13, should actually be 0.0 with sig figs. So, alright, let's move on to example 2. This one is also just a couple of steps, so not too bad, but the manipulation here is a little kookier. Here's what we want to get. 3H2 plus 1 ozone goes to 3 waters. Looking at my first step here, I see that I have 2 waters. That's pretty close, but I need 3. And there's no water here, so I know I need to manipulate that first step to give me 3 water. So what we're going to do is we're going to multiply the whole thing by 3/2, which is, like I said, kind of kooky. So we're going to get, that'll give us 3H2 plus 3/2 O2, and that'll go to 3 waters. Don't forget your delta H. We have to multiply delta H here by 3/2, so that will give me negative 725.4 kilojoules. Pretty kooky. Okay, looking at step 2, I have the ozone in this step. I only need one ozone, and I currently have 2. So what I'm going to do is I'm going to multiply the second step by 1/2. So that will give me 3/2 O2, my yield sign here, and only 1 ozone. Never forget to change your enthalpy. I'm going to multiply my enthalpy by 1/2 and get negative 142.3 kilojoules. So let's add everything together. We'll see here that okay, I think I saw an error that I did here. This is currently positive, so let's fix that. Now, as I add these together, like I was about to do, we'll see that nothing cancels out. So I need to get rid of these O2s. So what I've realized is that I made a mistake. It happens when you do Hess's law. And when you add them up, you always add them up to see if you actually did make any mistakes. What I need to do here is flip that third reaction around. And when I do that, that will change the sign back over here. So we're going to fix that oversight. That'll give us O3 and 3/2 O2, and we're back to the negative number over here. So now when we add these up, 3/2 O2 cancel, we get 3H2 plus ozone goes to 3 waters, and that's what we were looking for. The delta H for this overall reaction now becomes largely exothermic, 867.7 kilojoules. All right, let's move on to example number 3. We have 3 steps. So this isn't any harder, it's just a little bit more to have to deal with here and keep track of. So let's go through it. Here is the overall reaction that we're looking for here. The first thing I see is N2O. I usually go left to right. It's like I'm reading reading words. And I'm going to look for N2O. I see it in step 3. So you know what? For this problem, I'm actually going to start with step 3. I'm going to manipulate it first. I see that I need only 1 N2O, so I'm going to multiply this thing, step 3, by 1/2. So that's going to give me N2O goes to just 1 N2 and then 1/2 O2 with a delta H of negative 81.6. That's coming from multiplying delta H by 1/2. Alright, so the next one, in O2, I find it in step 2, so I'm just going to look at that one. For it looks like I need to reverse it to get the NO2 on the correct side, and I also need to multiply it by 1/2. Alright, and we're going to reverse it. So that's going to be NO2, yield sign, only 1 NO, and then also giving us 1/2 of O2. And this delta H, don't forget we flipped it so it becomes positive 113, then times 1/2. So that gives us 56.55 kilojoules. And then the last one, I don't believe we need to do anything at all with. Just looking at it, I can see that I have an N2 coming up that I need to cancel. So we're actually going to write this one down just like it is. I think it'll work. We'll cross it out just to make sure before we add the enthalpies up. So the enthalpy here wouldn't change. We're going to keep positive 180.7. All right, so let's add it up and let's make sure everything that we need to have canceled actually does it. The N2 goes away. Now I have an O2 right here. Does it cancel with O2 on the product side? Yes, because this one and this one is one O2, which would cancel there. So that would give me N2O plus NO2 and across. Now it looks like if you get in too big of a hurry that you only have two NOs, but don't forget about this one. So you actually have three NOs, and that's what we were looking for. The delta H for this reaction comes out to be, if I did my math correctly, 155.7 kilojoules. Now this last example is a much more representative problem for what you may see on the AP test. This problem is also going to segue us into the final part of this unit where we learn to use heats of formation. So I talked to you at the very beginning of this video about what heats of formation mean. It's the energy you get from making a compound out of its constituent elements under their normal conditions. So like on the AP test, they would give you this problem. Look, here's our question this time. Find the standard enthalpy of formation of gaseous diborane. Well, you have to know what that means. The previous three examples, it says the directions were, here's the reaction you're trying to get. Here are the steps you can use to get there. Well, this one, they didn't give you the reaction. You have to know how to write the reaction based on understanding what standard enthalpy of formation means. So at the top of the page, we're going to start with that. Diborane is made from two elements. Boron, which is a solid, plus hydrogen, and it makes B2H6. Okay, and we just balance it. So 3 hydrogens, 2 borons. Let's go ahead and put our gas here for hydrogen. Now we're having a solid plus a gas goes to all gas. Just think to yourself before we do this problem, is it going to be exothermic to turn a solid into a gas, or is it going to be endothermic to turn a solid to a gas? If you use a little common sense, you're going to think, well, this is probably going to be endo, so we'll expect to get a positive value. Now, we may not, but that's just something we can check as we work the problem. All right, now that we know what reaction we're trying to get to, we can take our steps. If we begin with the first thing, boron, in this first step, if I can multiply it by 1/2, we can get everything that we need. So we're going to have 2 boron plus 3/2 O2, and we will get B2O3. The delta H for that minus 1254.55 kilojoules. All right. Now I'm looking at this B2O3 that we just wrote down, this one right here, and I know that needs to go away. So I'm looking at my steps 2 and 3 to figure out which one to manipulate next. And I know I need to get rid of that B2O3, so I'm going to go to the third step, and I can see that I'm going to have to flip it around. It only has one B2O3. That's what I have written down already, so I'm just going to flip it around and not do anything else. So B2O3 plus 3H2O gives me B2H6. That's good because in my overall reaction I need one B2H6. And then 3O2. The enthalpy here, since we just flipped it, will be positive 2147. 2147.5 kilojoules. And finally, we look at that second step there and kind of think about what we need to do. I'm going to need to get, I believe we're going to multiply it by, what are we going to multiply it by? Let's see. I believe we've got to multiply it by 3/2 here. And that'll allow us to turn that 2 in front of the water into a 3. Alright, so that will give me I'm hesitating on this because I think there's a typo. I just caught it. This 3 shouldn't be here. That should be a 2. That would balance that equation. So I made a little bit of a typo there. So we're going to multiply that one by 3/2. And that's going to be the right answer. So sorry about that. So 3/2 times 2, that's going to give me 3H2. That'd be 3/2 O2. And then that'll be 3 waters. The delta H here, if I did my math right, 857.55 kilojoules. Alright, let's add this up and make sure everything cancels out. We talked about the 3 waters going away. There they are. The B2O3s go away. And then we have some oxygen that needs to disappear also. I have 3 oxygens over here. I have 2 3/2, so remember that's 1.5 and 1.5, so those together equal 3. So that they cancels out. So we're left with 2B plus 3H2 goes to B2H6. That's the overall reaction we were looking for. If all of my numbers were correct, hopefully I didn't make an error here. We got positive 35.4 kilojoules. And that matches our prediction in that it would be slightly endothermic, and that is what you need to get that that phase change and have everything go into a gas. Alright, there's some practice I'm going to leave you. 3 problems on your own. If you have any questions, come in and we'll work through them together.